Greetings, I'm Professor Seth Frey. Welcome to Module 8's code lesson on functions and functionality. Um, we've learned about how to build complex objects, representations of complex things in the world. That's what nested dictionaries have brought us, and lists of lists, or lists of dictionaries, or dictionaries of lists. This nesting allows us to create more and more involved objects that look more and more faithfully represent real world things. Along those lines, we've experienced flow code. You can kind of think code flow, our for loops and our if statements, and those things we've learned have allowed us to represent more and more complex actions. You can almost think of nested dictionaries as like real world noun, approaching the noun side of real world things, with complex flow control as representing the verb side of real world things. Now we're going to get more and more explicit into that with something called functions. You've learned about functions. You've been using functions since day one. Now we're going to define our own functionality. This means taking the most elementary building blocks of Python and making building blocks of our own that allow us to branch off in new directions and build, sort of new levels of meaning in code for our own specific kind of use case or problem or whatever we're taking on. Writing functions is a fundamental part of basic Python, and this is part of your foundation of establishing a kind of literacy in code. Absolutely, it's a really important part of it. And learning to think in functions becomes learning to think abstractly and in code, and therefore learning to represent the real world things in code. It's a part of it. So with all of that background in mind and that linkage to everything we've learned to date, we've got three objectives today. They're going to be how to define function zero and learn the syntax of function definitions. We are going to apply a lot of that in the pretty fun realm. It's not web science, it's drawing pictures. We're going to draw pictures using a little simulated robot that carries different color markers around. And that's going to illustrate a lot of the key concepts of what functions bring and what custom functions bring to any language, not just Python. One of those a key concept in there is going to be some jargon called refactoring that I'm going to highlight and dwell on a bit. The boilerplate for this lesson is going to be different. It's going to be a lot bigger and uglier. I have a mini topic lecture explaining why we've done that. But the rules are the same as before. You don't have to read it. You don't have to understand it. It's not going to be on the exam. It's just there. Skim it. See if you can kind of get the gist of what's going on in it. But at the end of the day, treat it like all the other boilerplate code you've encountered to date. Run it so that the rest of the notebook, the rest of your lesson runs as well. And with that, we can get into the definition of creating functions. So you already know what functions are in Python. You've been working with functions since day one. I think the print function was probably your first function. It's some word, it's got parentheses after it, and that kind of means it does something. And sometimes we put stuff in those parentheses, that means the function took input, sometimes it didn't. So Python has a lot of built-in functionality, but we can use all that to build more and more advanced functionality. That's a key concept, and we're going to learn it. So your first function, we're going to, here it is, it's called last char, and it's going to take some string and return the last character of that string. So instead of, you already know how to do that. You've learned about -1 indexing on strings. So before you were typing that, but that doesn't mean something. I mean, when you're good at Python, you can read it and you know just what it means, but it's not really that skimmable. Here's something that's a lot more skimmable, is last char. So instead of A, B, C, D, E, X, Y, Z, square brackets -1, we would do last char, A, B, C, D, E, X, Y, Z. That's kind of more meaningful. Now this is a really simple function, so you don't have to do that, but it starts to illustrate what function definitions buy us. Now let's dive into the syntax a little bit before we run it. So we have an indent block, and prior to every indent block in Python, we've got colons. But different what a colon what a block means depends a lot on what's behind the colon. Is it for blah 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 behind a colon? Is it if blah 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 behind a colon? In this case, it's def blah 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 behind a colon. Def is short for define. So the first thing you type is def. Then you type the name of the new function you want to create in the world. So somewhere deep in the source code of Python, it says def space print, and then it says open bracket, and it has some input, and it has close bracket, and it has a colon. So print is a function that was written. You're treating it as kind of a given, but it follows this exact same syntax. So then we put the parentheses, just like in we put them in the function definition in the same way we put them in the function call when we'll eventually use lastchar. The difference being when we call the function, the stuff in the parentheses is the input to that function. We're here in this line, we're calling the function and we're putting this content into it. But up here in the definition, the stuff that goes in are the placeholders. Just like, remember, our for loop has these placeholder functions. And where else do we have placeholders? We've got placeholders in, a lot of your variables are placeholders. So this is, a string here is a temp variable. And the way this is going to work is that when lastchar gets called, whatever's in the parentheses is going to get assigned to this temporary variable. And then, so a string is going to become A, B, C, D, E, X, Y, Z. And then this next line, and then we're going to go inside the code block, assuming that variable exists. So A, B, C, D, E, X, Y, Z. The -1th element of that is going to be Z, and we're going to return it. This is the last part of function syntax. You can have we're going to find bigger functions that do lots of other stuff. Print, do stuff, and then lots and lots of lines like that. And then your function is going to tend to end, the last line of your function is going to tend to say return, open parentheses, and then whatever you want to give back to the user, whatever you want to be the output of running this. So we're going to, now if I just try to run lastchar without defining it, and hey, error, that doesn't exist yet. It doesn't exist in this world. It's a custom function that we're adding to the world with this def syntax. So we're going to run it, it's going to work, and now we're going to get Z back like we expected in the very beginning. So there were lots of steps to this. We started with def. When Python read this, it didn't do anything except that it added to its memory that, okay, now I know if I see lastchar occur somewhere in code, I know kind of that refers to something that I should look more deeply into when the time comes. So that's all that def does. There's no such thing as a string yet. A string's never been evaluated. The last element of a string has never been dug up. None of that's happened. We're just defining what will have occurred if we encounter code that has lastchar in it. So so we run this and something gets added to memory, but no actions occur. No actions occur until this line here. Now the computer's reading L. It doesn't really know what L is, and it's not at the end of the word, so it's going to keep reading till it hits this. And it's going to be like, okay, yeah, actually, I've seen that before. I know there's instructions I should follow when I see this. And I happen to know also it's a function, so I expect a parentheses, open and closing parentheses, and hey, they're there, so I feel good. Hey, inside that parentheses, there's some stuff. Hey, that corresponds to what I was told over in the definition up here to expect. So I'm going to assign this content to this temporary variable. Then I'm going to do the stuff to it. Get the last element of this input string, and then I'm going to return that to the screen, to the user. So that's Z, so we get Z when this runs. All of that happened. And so if you want a more kind of careful or deliberate look through the parts of a function definition, I've written it all out for you, and of course, happy to answer all questions. So that's enough to try a bit for yourself, understanding the parts of a function definition. what a custom function does, how it is or isn't like functions you've seen before. All right, and then we'll pick up after that. Okay, so now that you have the basic parts of a function, I'll give you a bit of a sense of which of those parts are always necessary, which are only sometimes necessary, and how does what you include, depend on what you want, what your goal is. So first thing to know is functions are flexible. Not all the parts I introduce you to are necessary. For example, not all functions have an input. If you've ever typed blah, 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 open, close parentheses, if you've seen that, what that is calling a function without input. In other cases, functions, they'll take input, but they won't actually do anything. They won't have a return value. They might do something else, but they're not going to return something. As in, you couldn't call it and assign the output of that to a variable because it didn't return anything. That function did something that didn't involve a return value. That's kind of abstract. It's important to know. You don't kind of get why that's valuable or important or what that has to do with anything until you've had a couple more years or courses under your belt. But it is something you'll encounter, so I'm telling you about it. To make this concrete, we've got here a function called 5. What does 5 do? Well, it doesn't take an input. I can tell you that because it has empty parentheses. What it seems to do is it defines this temporary variable called the number 5, which is the sum of 2 and 3, and it returns it. So what seems to happen is I'm going to call the function 5, I call it here, and it's going to return 5. Okay, now what did that buy me? How does that, what can I do now that I couldn't just do by typing one character, 5, instead of 6 characters, F-I-V-E, open, close parentheses? Nothing. This is an illustration of a basic idea. And with these minimal examples, you get the best possible sense of what parts are necessary and how parts connect to each other. We'll get to more complex functions. Just like a function doesn't have to have an input, it doesn't have to have an output. So for example, the function greet here takes this input and it prints out hello, but it doesn't return hello such and such. It just prints to the screen hello such and such. But I couldn't assign this to a variable. Again, that's kind of a subtlety. It's just important to know not every function will end in return. Those that don't end in return don't return anything. So when we run this, I should be able to greet Miriam. Hello, Miriam. So if a function is defined to take 0 arguments, you should give it 0 arguments. You shouldn't give it 1 argument. If it's defined to take 1 argument, you shouldn't give it 0 arguments or lots of arguments. So however many arguments are in the definition, that's the number you should send to it to get it to work. If you don't do that, you'll get an error. So here we've defined greet to take an argument, the name, but if we run it without one, we'll get a specific error. What's it say? Greet is missing 1 required positional argument, name. That's actually one of the more readable error messages in Python. It's telling us we sent it no arguments, but we should have sent it 1 argument. Similarly, 5 I'm supposed to call with no arguments. If I call it with 1 argument, with 1 input, I'll get that it takes 0 arguments, but was given 1. And then if I want to send greet several arguments, I'll be told, it should have gotten 1, but it was sent 2. All of these are errors kind of for different variations on the same basic reason. So you have to get the arguments right. Whatever your custom function demands, that's what you should send it. That's in terms of number of arguments, but we also have to think about type of argument. So different arguments deal with different variables or different functions, deal with different types of things. So we encountered upper. Upper takes a string and returns a version of that string that's all uppercase. If I was going to send a number, well, there's not really a meaningful thing, uppercase numbers, lowercase numbers. That's not really an informative construct. And so upper is not defined for numbers. It's defined for variables. So if I try to give it a number, I should get an error. That's the same for temporary functions. So for custom functions, for function definitions, for everything that happens in a function. So we're defining a function here called toProperName. What it should do, it takes an input, it takes a name, It creates a different temporary variable that takes the very, very first character of that name and uppercases it, and then appends the rest of the name. The rest of the name is everything from index 1 on to the end. And what it should return is the uppercase version of that name. That'll be great. So we'll define it, we'll run it on Caroline, lowercase, and what we should get back is uppercase Caroline. Look at that, uppercase Caroline, just like we expected. Now, if we send it something else, if we send it 4, well, here's what's going to happen. 4 is going to get assigned to name. Name is going to ask for its first element, which the number 4 doesn't have a first element because it's not a collection. And even if it did, that first element wouldn't be a string, so upper would fail. So we should expect a lot of errors. And when we get the error, Python, even though we ran this problematic code, Python's actually going to tell us that the error occurred here because the code's moving around. This is where code flow gets really complicated. We're no longer just looping or skipping lines. We're actually jumping around our code now. That's one way that functions make code more complicated, is you end up jumping all over your code. But Python can keep track of it, which is why when we get this error message, it's going to tell us all the places the code went wrong. It's going to say, well, in the grand scheme of things, the line that went wrong is the line we just ran, this one, to proper noun 4. However, if you really want to be specific about it, what about that went wrong? Let's look at this second block of error message. Actually, what went wrong is this specific line right here. So this is called a trace, where it tells you the most sort of proximal or near to you cause of the error, and it goes deeper, deeper, deeper to actually also show you the root cause of the error. And it shows you all the steps in between, if there were lots of steps in between. Int object is not subscriptable. Well, that's actually kind of an interpretable error message as well. I think I told you. 4 will get assigned to name. Name will get indexed, and then whatever gets returned from that index is uppered. But 4 can't be subscripted because 4 is not a collection, it's a number. Int object is not subscriptable. That's what that means. It's actually kind of legible, and that's not typical of error messages. They're usually kind of opaque and hard to understand. Another thing to know about functions is, the basic thing I showed you how they can take 1, but you've used commas inside of parentheses before when calling functions. You've sent multiple arguments to a function, and you're allowed to do that. If I want a function called addition, it would take one number and a second number, and then inside the function it would add those. In this case, I've defined a function called same length. It takes 2 lists, and it tells me are they the same length or are they different lengths. Def, same length, one argument, comma, second argument, close parentheses, colon. I'm going to define a temporary variable here that's the length of the first one, another that's the length of the second one, and I'm going to return the Boolean. I'm going to return either true if they're equal to each other, because this is going to evaluate to true, or false, because this will evaluate to false if they're not the same length as each other. And once again, if I run this before defining it, I should get an error. Same length is not defined because I haven't run this yet. See, it says that, name, same length is not defined. When you get this, it often means there's a code block you forgot to run. So now I'm going to define it, I'm going to run it, and what should I expect? Well, I'm taking 2 inputs. 0, 1, 2, 3, the list 0, 1, 2, 3 is one input. It's one thing, it's one list. A, B, C, D is a different single thing. It's a single list that has 4 things in it. The length of each of those is 4, so I should expect same length to return true, because 4 is equal to 4. And look at that, I get true. So play around with these variations on function calls and function definitions, and we'll pick up from there. So there are more subtleties to functions. They're creating, in a sense, these little worlds. The block inside of a function is isolated from the rest of your code. It's different from the rest of your code in the same way that the block under a for loop or the block under an if statement is sort of operating under different rules from the rest of your code. To pin that down, let's look again at our to proper noun function. Now we'll run it. So what we're doing in here is we're naming this temporary placeholder variable and then returning that. I could have just returned that, but it's sort of nice I introduced this intermediate step of taking that, assigning to a variable, and returning the variable, because that's more readable. I couldn't like glance at this right away and tell you that it takes a name and uppercases it and turns it into a proper noun. But this, it's probably the proper version of this, right? Its proper subname is the capitalized version. Like I can look at that instantly and have a really good sense what it means. So here's a question for you. In this function, I defined proper name. So does proper name... so to proper noun, that function now exists. I can call that function with stuff and it'll work. Does proper name exist? Let's find out. So I've got print proper name here, and if it exists, I'll print out something. And if it doesn't exist, I should get an error saying it doesn't exist. Okay, it says proper name is not defined. Well, I don't know. Maybe that's because I haven't called the function yet. I haven't called to proper noun yet. I actually did, but if we call proper name, if we call proper noun, then proper name up here is going to get assigned the value of Henrietta capitalized. And so when I print proper name, you'd think I would get that. But again, I print it and I get the error. So what's going on? What's going on is that to proper noun, everything in this block is its own kind of isolated world. It exists in jargon in its own scope, its own kind of reality. Things defined in that reality are useful in that reality, but as soon as you leave that code block, they stop existing. Now this is a technical point. It's called a scope. Is of great interest to real computer engineers, real computer scientists. It has all these implications. It's always something you have to keep in mind. It works differently in different languages. You don't have to think about any of that. I'm just introducing you the idea, one, because it can be a source of gotchas. I just want to give you a sense of what should happen in this language, in this situation. Also, it is a nice illustration of the idea that your functions are siloed. They're often their own little thing. They work in their own little rules. They're limited in how they interact with everything else in a way that makes them easier to think about. It means that when you define a function, you just have to think about that function. You get to think about the inputs going into it, the stuff going out of it. But you don't have to think about all the other stuff you have to do. That's nice because humans are limited. So when we build stuff, we don't want to have to be thinking about everything. We want to be able to, the best situation for a big problem is that it can be divided into lots and lots and lots of smaller problems. If you can divide a big problem into smaller problems, then you can solve really big problems, really big, impressive looking problems, because they're nicely decomposable. We never would have gotten a spaceship to the moon if we couldn't have decomposed it into lots and lots and lots and lots and lots of small, tiny, human solvable problems. That is what, if you ever want to know what engineering is, that's what engineering is. And that's why computer science is considered a branch of engineering, because we take, instead of physical problems like building a bridge, we take conceptual problems like writing a program. And building that program is the process of learning how to cut it into smaller stuff. This isolation that functions have from the rest of the world helps enable that breaking down of things. So this is what scope is, and this is how it works. Play around a little bit with scope means, with what intuitions you should get now that you have this idea in place, with what it means for functions to have their own little world, and then we'll pick up from there. So I introduced functions with this metaphor of building blocks, that Python gave us these elementary functions that we never saw definitions for. We just sort of learned what they do. We learned what you put in the parentheses. And from those, I said those are building blocks from which we can build more complex building blocks. And those more complex building blocks, we can bring them together to build even more complex building blocks, and thereby, build levels of meaning or levels of abstraction and get closer and closer to faithful representations of the things in reality that your code kind of corresponds to or models. I introduced that, but that's a lot of metaphors. It's very high level, so we're going to pin it down. I'm going to walk you through the process of building blocks out of building blocks and building building blocks out of the building blocks. You build out of those building blocks. And we're going to get closer and closer to meaning, closer and closer to like interesting things. We're going to do it in drawings. And we're going to, in a specific type of drawing, it's going to be called turtle drawings or turtle graphics. The basic idea of turtle graphics is the turtle. A turtle, imagine, you can buy them actually. They're these little robots. They've got 2 wheels, and they carry around a little marker behind them. And now, if both wheels move forward, it goes forward. If both wheels move backward, it goes backward. If one goes forward and one goes backward, it'll turn, or turn the other way. So it can move each of its wheels independently to go forward, backward, left, or right. Additionally, its marker in the back, its pen, that can be in a raised position or it can be in the down position. Now, if by default the marker is raised, if the marker is down and the turtle moves around, it'll draw a line because it's dragging the pen behind it, around around the world. Let's say all of this is happening on a big piece of paper. So with this very simple thing, we can add that maybe it can change what color pen it's holding. So we add those things and suddenly we can draw pictures. So what would that look like? Well, let's give the turtle instructions that would result in a drawing of a square. So let's see. I'm the turtle. Here's my pen, it's up, and I'm in a starting position. So what's my first instruction is you're going to tell me to put my pen down. So I'm going to put my pen down. Then you're going to tell me roll forward 5 inches. So I'm going to take 1 step. Then you're going to tell me, what does it say? Turn right 90 degrees. Which way is right? It's this way. Actually, I'm going to go left. Then it's going to say, I haven't actually... so far I've drawn a line, a 1 step worth of line. So now I'm going to go 1 step forward, then I'm going to turn right, then I'm going to go 1 step forward, then I'm going to turn right. Right now I've drawn like a U shape or an N shape, whichever way's up. Now I'm going to do 1 step forward, and I'm back where I began actually. The last instruction is to turn right 90 degrees, so I'm facing the original direction, but that didn't actually do anything. I had a square at this point, I still have a square, and then pull your pen up. This also doesn't change the drawing, but it's nice to end up right in the exact same state I began. I began in this position with my pen up, I ended in this position with my pen up, facing the same direction. So, by giving our turtle lots of these little instructions, move forward, move backward, turn left, turn right, pen up, pen down, we can build more complex stuff. In this case, we built the idea of a square. A square of a specific size and a specific location, so not a general square, but a square nonetheless. And we can draw more and more stuff. So first, let's do exactly what we did, but the code version of that. So how do we actually do this in code, follow these instructions? Well, here's the Python that corresponds, and we'll build up to a square. So the first thing we do, I have this function for you called initialize turtle. What it's going to do, it's going to create a canvas, and it's going to create a turtle in the middle of that canvas. The canvas is going to be 800 by 500. This output, you don't have to understand it. We will get there. We get a picture here once we actually try to do stuff. We're going to initialize turtle, then we're going to take the pen down, then we're going to move forward 200 pixels. The canvas we're defining is going to be 800 wide and 500 tall. We're going to start right in the middle of it at coordinates halfway through 800, so 400, and halfway through 500, so 250. Our starting position is 400, 250. We're facing up, so we're going to walk up 200 more pixels. What's that position? That's going to be 500 tall, at 200 that's 450 tall, out of 500, so we're going to be pretty near the top. Then we're going to turn left 90 degrees, then we're going to go forward another 100 pixels, then we're going to lift the pen up. So we're going to draw a sort of backwards R kind of shape. I'm going to run this, and there. We started in the center of the canvas. You see how big the canvas is? Yeah, the canvas is about that tall. From there to there. We start in the middle. We start facing up. We start with our pen up, we put the pen down, we walked up 200, we turn left, we walked over half that distance, and we get the shape. Okay, so these are all this text here describes a lot of the ground rules, just so you can kind of get your head around it. I'm going to introduce, just like there's a left function, there's a right function. Just like there's a forward, there's a backward. So now we can build up to a square. And we're going to do just the same thing we did before. Seth, I'm the turtle now. Seth, put your pen down, walk forward, turn left, walk forward, turn left, walk forward, turn left, walk forward, turn left. I think that was 4. Do it 4 times. Then lift your pen up. And it looks like this is where the turtle began, and this is where the turtle ends up, facing in the same direction. Up, turn, over, turn, down, turn, over, turn. In every case, forward, turn, forward, turn, forward, turn, forward, turn. Again, and these are simple instructions, but we can build more and more complex stuff. What are other things we can draw? Play around with the different kinds of instructions we can give, get a sense of this basic layout, the basics of the canvas, the turtle, these most elementary instructions, and we're going to start to build more and more complex meaning. Okay, so let's say I wanted to build, to draw 100 squares. All those instructions I typed, I'd have to type them over and over 100 times. It was about 10-ish lines of code times 100. That's 1,000 lines of code. I don't want to do that. Furthermore, if I write all that code and then come back 6 months later and look at it, I see a lot of forward, a lot of left. It's going to take me a while to know what it means. It would be great if I could take all those 10 lines of code and just sort of tag it or label it as meaning square. And then from then on, just instead of referring to the instructions, refer to square, this idea, and let the instructions handle themselves. That's good for the amount of typing I have to do. It's good for readability. It's good for communicating with others. It's good for remembering what I did in the future. And it's good for errors. Those 1,000 lines, I've got, that's 1,000 opportunities to make a typo. Whereas if I can get it down to 100 lines, that's 1/10 as many opportunities to make typos. So for all these reasons, it would be great if I could chunk meaning. So that chunking meaning, like just to give you an example of what I mean when I say come back to code and have no idea what it means, what does this do? At a glance, well, it looks a lot like our square code, so it probably draws a square. But I kind of have to look closer. It's not going 90 degrees anymore. It's going 144 degrees. What's that? There's not 4 of them anymore. It's 1, 2, 3, 4, 5. So I drop 4 coins on the ground, 5 coins on the ground. It takes me a second. I kind of have to. Some people can just tell 4 from 5. I sort of actually have to count to see if it's 4 or 5. I don't know. That's called subitizing. Word of the day. So I can't subitize 4 or 5. I couldn't tell that that's 4 instructions instead of 5. The skimming doesn't work. So the best, easiest way to find out what this does is going to be just to run it. Let's run it. What happens? A yellow star. Okay, so apparently 144 degrees corresponds to a star. Our turtle started here, walked forward 200, turned to 144 degrees, which is that much apparently. Then walked forward 200, then turned the same amount, walked forward, turned, walked forward, then turned back to face the original direction, which was all turns of 144 degrees. Okay, great, I know that now. Do I want to remember the number 144 for the rest of my life as how you draw stars? No, I want to abstract out of the specifics of how it got drawn and just keep the word star in mind. I want to solve 144 once by trying all the other numbers until I get a star, and then once it's solved, I don't want to think about it again. So for all these reasons, functions are super valuable. Let's show what that looks like. So we're going to define a function called star. It's going to go forward 200, left, forward 200, left, 5 times. When I run this, star now exists, and my instructions that were, about a dozen lines, now they're just a couple lines. And in the space it took me to draw 1 star, I can now draw 3 stars, all of different colors. We're going to initialize the turtle. That sets up the canvas. We're going to set the color of the pen to yellow. Pen down, draw a star, pen up. Then we're going to go somewhere else. You're allowed to use this function go to. It takes an x coordinate, that's 200, out of 0 to 800, and a y coordinate, 200, out of 0 to 500. We get to go somewhere, change the color of the pen to red, draw another star. then go somewhere else, change the color of the pen to blue, draw another star, pen up, pen down, pen up. When we run this code, we will get 3 stars. Very nice. So by developing this abstraction, our code became more readable, more efficient, more expressive. Now we can do a star is now an abstraction that I can make hundreds of copies of without a lot of extra thinking. All right, and a great thing about functions is that we can add more and more complexity. With the previous instructions, we were always going forward 200, forward 200, forward 200. Well, and if I wanted to make a star of a different size, I would have had to make a different function that instead goes forward, 10, forward 10, forward 10. I don't want to make, if I want stars of 100 different sizes, I don't want 100 different functions. What if I just had one function and it takes an argument that corresponds to how big the star is? So that's what we're doing. We're going to overwrite the previous function star, and we're going to replace it with this function star. The old one took no arguments. If you had given it an argument, you would get an error. This one takes one argument, side length. It's a placeholder variable. And if you try to send star, now if you try to send star no variables, you'll get an error. It'll only run correctly if you send it one variable. So we'll initialize, we'll change. We're doing the same thing before. 3 equal size stars, yellow, red, and blue. Pen down, star, pen up. The difference being is now we're sending star an argument. The first one we make a small star, 300. The second is going to be the same size as before, and the third is going to be bigger. So this code is different in one way. We're now passing an argument to star. And what this little change bought us, just replacing all the 200s with side length and adding side length here, what this little change brought us, again, is more and more expressivity. We can do more and more abstract things. And in the process, we're getting further and further from the turtle. If you remember, we had the color function, it's an instruction to the turtle. Change what color of pen you're holding. But when I run it this way, right here, what if I pull color into the function and I add a second argument for color? That way, when I run this, now star takes 2 arguments, and now when I run it, I'm now calling a function called star that takes how big the star should be and what color it should be. I'm further and further from any memory that how this is implemented in terms of turtles. That it's turtles all the way down. I don't have to think about that. I'm getting abstracted further and further from the implementation, which gives me more and more of the luxury to think in the high level. So while we're pulling stuff out, let's take a look. What's something here, let's say I'm just sick of typing, sick of all the redundancy, my fingertips are sore, I've got carpal tunnel. What's something I'm just typing over and over here that I don't want to type anymore? Well, initialize turtle, pen down, star, pen up. Go to this, pen down, star, pen up. Go to here, pen down, star, pen up. That pen down, pen up, that's closer to the turtle. It's not closer to the meaning of what a star is. It doesn't help me understand a star better to have pen down, pen up here. It's not like I'll deviate from that. To draw a star, the pen's always got to be down before I start, and it should always come back up after I end. So how about we pull pen up, pen down into the function definition. Pen down, color, do a bunch of stuff, pen up. So function now does that. It's still taking the same number of arguments, so we still call it in the same way. But at this point, I'm drawing 4 stars, and our code is shorter than it was when we drew our first star. I run this code, I get 4 stars, all of different sizes, very clean and nice. And I don't even remember that turtles are involved anywhere. So we've gone to more and more abstract meaning, fulfilling this idea of building abstractions on top of abstractions. We're going to keep pushing that. And the luxury here is just like the car example, that you don't have to know how a car works to drive it. You shouldn't have to know how a car works to drive it. You should just get to type star and it'll draw a star. You shouldn't have to remember all your pens down and pens up and color of pen and location and all that. So by functions give us this level of abstraction, this abstraction layer that gives us the luxury to think about things we want to think about, high-level things about what picture we want to draw, and avoid all the nitty-gritties that confuse us, that create errors, that throw us off. play around for a little bit, and we're going to pick up from there. This all is going to bring us to some jargon, refactoring. That's a pretty ugly word. What it means is something we've done. Let's say I was typing out all those instructions for all those 100 squares, and eventually I realized, oh wait, if I just put those 10 instructions into a function, then I only have to type the word square 100 times instead of all the instructions 100 times. Refactoring, we did it with star. It's identifying that you're doing something over and over again, that you're literally typing the same code, and that if you just pull all those instances out from all other places in your code and put it all into one place, one function, you can replace all those lots and lots of instructions in all those places with that single function call. And that's good for all the reasons that functions are good. Improved readability, improved memory for why you did it, improved abstraction, reduced errors, because again, I could have introduced an error any of the 100 times I wrote out all the instructions for square. Now they're all in one place, so I can only screw them up once instead of 100 times. We're going to pin refactoring down and show more and more dimensions of it, because you don't just have to, you can even refactor within your own functions. You can build functions out of functions out of function and build more and more levels of the pyramid in your abstraction layer and get closer and closer to higher and higher level meaning. So, what does this code do? Well, it draws a star. It starts with a star. Then it draws something with, looks like 3 sides. Then it draws something with 4 sides that turns 90 degrees. Then it draws something with 6 sides that turns 60 degrees. I'm just going to guess. I'm seeing 120 degrees, 120 times 3, 360, 3 sides. I'm going to guess the second thing is a triangle. First thing's a star, red star, green triangle, blue square, and orange hexagon. I'm like skimming. And there's no meaning here. There weren't hints. There should be hints. These should correspond to functions. But yeah, I guessed okay. I did pretty good. If we pull those into functions, then that code's a lot easier to read. It's a lot shorter. So we're going to define a star function. This is the same star function as before. It's got pen down, color, and pen up in it. I'm going to copy that code and then just paste it here, and then change the number of sides, change what angle gets turned, but pretty much leave everything else. Oh, and change the name. I'm going to call it triangle instead of star. So I changed the name, I changed the number of times this repeats, and I changed the amount I turn left. And now I'm drawing a triangle. Now these are instructions for a triangle. If I copy these to here, bring it up to 4 sides, change the angle, create very repetitive, kind of well-understood changes, now I have 3 functions. And my code down here becomes a lot shorter. I've got a triangle and a square. And I can start to do higher level meaning. So we did it a little differently. We didn't draw the same picture as before. And I introduced this function called face. So the turtle, in addition to having a location, has a heading, has a direction. Face 0 points in the direction, is going to point us to the right. So we're going to point to the right. We're going to move to this location, which is this corner right here. Then we're going to draw a triangle. Boom, forward, turn, 60, forward, turn, 60, forward. Then we're going to go to this location here, face 0 again, face over, and draw a square. What do we get? We get a Christmas tree. Later on, we're going to define a Christmas tree function, and it's going to just run this code. So we have so if I want to draw lots of Christmas trees, I don't have to call triangle, square, triangle, square, triangle, square. I don't have to remember all the go-tos, all the faces. No, there's this idea of a Christmas tree. It just so happens it's built out of lower level stuff, which I defined. I totally forgot how all that stuff works, and it doesn't matter because I'm living in picture world. I don't have to think about the specifics of turtle world. This is good. The refactoring. Let's look at things I did in here that were too much typing. Actually, my actual instructions, they were not too much typing. That was pretty efficient and short and nice and clean. But you know where there was a lot of typing? This was boring. Forward, left, forward, left, forward, left. Forward, left, forward, left, forward, left, forward, left, forward, left, forward, left. You've already seen ways of reducing the amount you type especially if it's the same instruction over and over again, that's got for loop written all over it. So we're going to rewrite these functions, or at least these two, but I think all three, in terms of for loops. There you are. So this is the same instructions as before. Pen down, 2 arguments, star function, 2 arguments, pen down, change the color. All we're doing now, and then there's forward, left, forward, left, forward, left. But instead of typing out forward, left, forward, left, forward, left, I just put them in a for loop that repeats 4 times. Range 5, if you remember. The range function, you give it a number, it'll send you through the for loop that many times. And this star draws the same star, except it's a lot shorter. There's less repetition. And what we've got here is a square function that's doing the same thing. Pen down, change the color, loop a bunch, pen up. I go forward by side length, and I turn left by 90. 360 divided by 4 is 90. Why didn't I just type 90? Why did I type 360 divided by 4? We'll get there. Triangle, same thing. Pen down, color, loop, pen up. The only difference here, the only difference of this from star is that I'm going 4 times instead of 5 times. The only difference of this from square is I'm going 3 times instead of 4 times. And I'm going a different angle. I'm going 120 degrees rather than 90 degrees. But this is a star function that works the same way as before. These are square and triangle functions that work the same way as before. And then if I rerun this code, it's still gonna. If I try to draw a triangle Christmas tree again with the same instructions, the details of the implementation don't matter. The fact that I'm using a for loop doesn't matter. It was nice. It saved me time. It's a little more elegant and shorter and concise. But at a high level, if I'm just thinking in Christmas tree land, I don't think about other stuff. I don't really care. If I didn't write it and I don't have to see those details, I don't care if you use the for loop or not. However, it is going to be nice that we use the for loop for this reason. I want you to look at these 2 functions. I said they're really similar, and they're really similar. There's only 2 things that's different about them. And really, in some sense, only one thing that makes these functions different from each other. These lines only differ in name. Square versus triangle. This line's the same. This line's the same. This line's only different because one's a 4, one's a 3. This line's the same. This line's only different because one's a 4, one's a 3. This line's the same. Okay? This says 3 and 3. That says 4 and 4. Every other character of those definitions is the same. So this is really where the insights, refactoring corresponds to insights. Refactoring is this operation of noticing repetition and pulling it out. The insight is realizing that there's an abstract structure to a problem and that you're getting closer and closer to it. The fact of repeating yourself constantly is the fact of noticing abstract structure. What got repeated in this instance? Literally, all of this code got repeated. All of this code got repeated letter for letter except for 2 things. And this is where arguments come in. What I could do is if I just added 1 argument to the front of this, or the end of it, whatever, for number of sides, and replaced the 4 and the 4, or the 3 and the 3 with that variable, with that placeholder, with that argument. Now, I love this. All I have to do, I could just draw a shape function. It takes 3 arguments, side, the other 2 are the same, side length and color. This is the exact same code as before, but I've replaced the 4 or the 3 with sides, number of sides. And now what I can do is my triangle and my square function, they're shorter than ever. We thought they were short before when I used the for loop, but now they're 1 line. All they do is call shape with argument 3 for the triangle and with argument 4 for the square. Now, doing this took a little bit of knowledge of geometry. Like we had to know that the interior angles of a regular shape always sum to 360. That's why our turtle is always facing the same direction that it started in at the end of a shape, because it's gone 360 degrees. That's the geometric intuition behind this 360 rule. So we had to do a little bit to know that 90 is the same as 360 divided by 4. That 120, which is the inner angle of every, or the amount you turn for every part of a triangle, is 360 divided by 3. But yeah, it's the outer angles. The amount you turn to draw a shape, no matter what shape it is always going to be, for a regular shape, is always going to be 360 degrees. That's our little bit of geometry, so we cheat a little bit, but we got this great benefit from that little bit of knowledge. So now, square is a function defined in terms of regular shape, which is defined in terms of forward and left. So we're getting more and more abstract meaning. And when we add Christmas tree on top of that, Christmas tree is defined on square and triangle, which are defined on regular shape, which are defined on forward and left. More and more abstract meaning, more and more high-level meaning, more and more distance from like the specifics of a turtle, and more niceness. So refactoring gives you, it both has the practical benefit of less typing, kind of, shorter code overall. It's better access conceptually to like the underlying consistencies of the system you're trying to model or represent in code. And there's these little moments of epiphany, these little discoveries you make of like, oh wait, this is actually the same as that, except for this one thing, which I can pull out into a variable. Those are like a lot of the rewarding moments of code, is realizing that type of thing. So we're going to play around with both of these sides of refactoring in the try-it blocks, and then we're going to pick up from there. So we're ready to bring it all together. But first let's reflect a little bit. This regular shape thing, we pulled the essence of what a shape is out of both our square function and our triangle function, and then redefine square and triangle in terms of the more essence of what a shape is. And that's cool, like as an intellectual exercise. But did it really buy us anything? I mean, it wasn't that much typing to do 2 for loops instead of 1. I'm going to make the argument that it does buy you something. That by identifying these consistencies, these patterns, by abstracting more abstract meaning out, and giving its own representation, that you get new ideas for free. If you think about it, now that we've done that with regular shape, we can draw triangles, we can draw squares, we can draw any other shape as well. We can now draw we get hexagon for free. Hexagon's a freebie, decagon's a freebie, dodecagon's a freebie. But what about circle? Circle seems like a really different kind of shape than square or triangle because it's curvy. So let's think about it. How are we going to draw a circle? Well, what I've told you is when you face a complex problem, solve a simpler one. What that looks like in code is, okay, circle's hard, but I can do a line. So I'm going to do a line. Okay, I figured line out, now I'm going to do triangle. Okay, I figured out triangle, now I'm going to do square. Okay, I figured out triangle and square. Now I'm going to write one function that can draw all the shapes. Once I've done that, a circle, if you take a magnifying glass and go really close into it, if you take this sort of calculus view of a circle, it's sort of just like a bunch of really tiny lines, and you move just a little bit. So I'm going to argue because we abstracted triangle and square into regular shape, we got circle for free. What's circle? Circle is a regular shape that takes 360 sides. And so it's got 360 lines, and after every line you move 1 degree, 1 degree, 1 degree, 1 degree, 1 degree, all the way around until the turtle, have rotated 360. So let's run it and see if we drew a circle. And our code now is like 3 lines. This is crazy. It should have been 360 times 2. Forward, turn, forward, turn, forward. It should have been over 600 lines. We got it down to 3 lines because we defined circle, which itself only took 2 lines to define circle. So all of this, what do we get? It takes a bit because it has to draw 360 lines. So thanks for a little bit. There we are. Hey, look at that. It's moving around. Oh, finished the circle. That's rewarding. All right. And this is our big takeaway, our abstract meaning. We're going to draw a Christmas tree function. We're going to define Christmas tree function. It consists of an orange square that's going to be the base, a big green triangle that's going to be the top, and we're going to draw a little star on top, use our old star function. That's so nice and like seasonal. It depends maybe it's timely depending what term you're taking this in. And now we get to draw a whole scene. So here's our scene. Using all these different things. We're going to draw our Christmas tree, but that's just the beginning. We're going to draw a bunch of presents, different color squares at the bottom of the tree. We're going to draw some ornaments using circle. And we're going to draw a banner. There you see the banner's already drawn. We define a bunch of colors. Then we use a for loop to draw a bunch of triangles next to each other. And here is our holiday-themed giant takeaway. We started with pen up, pen down, forward, backward, with this image of a robot. At some point during this lesson, you stopped thinking about the robot. You started thinking about triangles and squares. You abstracted out of the specifics, and then we built a layer on top of that. We built a layer on top of that. We built a layer on top of that, and now you get to think in MS Paint, and you're starting to think of all the things you do with your little Paint program. You can now do in Python. So this was all possible because of functions, because of defining custom functions. Our def abilities. Help us draw functions and help us imitate Paint by the end of just one lesson. So we can add custom functionality to Python by defining functions on top of functions to do more and more complex stuff, more and more like stuff that's conceivably useful. We discovered how to define functions of our own. We made all that concrete in Turtle Graphics, and we experienced this ugly jargon refactoring as like a useful concept that gives us access to real meaning. All of that's, I think, pretty cool. So congrats on making it through. And that's the end of that.